My name is Caetano Miranda. I'm the Director of the Education and Diffusion of Knowledge of the RCGI, the Research Center for Greenhouse Gas Innovation, one of the leading engineering research centers of FAPESP. Today, our RCGI Colloquium series is broadcasted live from São Carlos, from the University of São Paulo in São Carlos. And it's a pleasure to have Professor Anthony Kucernak from the Imperial College London. I'm going to give to ask to Professor Thiago to comment on our program on the spec and introduce our speaker. Thiago, please.
Good afternoon, everyone. It's a great pleasure to have or to host Professor Anthony here. We think this is an official activity of a spec project from FAPESP entitled From Fundamental to Applied Science, New Frontiers in Fuel Cell Technologies, having the PI as Professor Nigel Brandon and the host PI, Professor Giulio Meneghini, both who idealized this. And we have a great team of professors from Imperial College and from the University of São Paulo, like Professor Caetano, Professor Hamilton, and Professor Anthony is here for the first time within this special project. And for me, it's a great pleasure to host him here at RCGI, and I'm quite happy with our colleagues at the Institute of São Carlos, the Chemistry Institute there, to host him there as well on these activities, because I've worked with him some years ago while I was working at Imperial College London, where I met also Professor Nigel. It's a great pleasure to have Professor Anthony here, and I kind of ask Professor Edson Cianelli to introduce and give a brief biography of Professor Anthony. Edson, please introduce Anthony.
Okay, good afternoon to everybody from here in our amphitheater, and then people from RCGI. I am Edson Cianelli from Institute of Chemistry of São Carlos, and it's a great pleasure for me to introduce Professor Kucernak for this colloquium. Professor Anthony Kucernak is a professor of physical chemistry in the Department of Chemistry of Imperial College at London, and has respective experience in the study of various aspects of solid polymer electrolyte fuel cells, capacitors, and the design of new electrochemical techniques. His group currently studies a large number of aspects of fuel cell systems, ranging from the development of new electrocatalysts, the development of new techniques to characterize and study electrocatalysts, and the development of fuel cell electrodes, and finally the development of new methods to characterize fuel cells. We had some interaction in the past through the stage of Thiago in our laboratory, by which we could receive a student from College Station to do some single cell measurements in the past. Okay, this is what I have to say. So I'm pleased to call Professor Kucernak to provide his speech. Thank you.
Thank you very much. And thank you for the University of Sao Paulo and for FAPESP for giving me the opportunity to actually come here, and actually give these sorts of presentations. And also, here in Sao Carlos, the people here have shown, a lot of warm friendship, and of course also the people at the RCGI as well, who I'm hoping that our opportunity to actually collaborate together will actually blossom, and we'll have lots of fruitful research done. I'm going to talk rather than focus on more fundamental research, because we had a discussion here earlier on today where I gave a talk about more fundamental aspects, I thought today it might be more interesting to discuss a little bit about some of the viewpoints, especially from a European, a UK and a European perspective, about the need for storage of energy at large scale. And, this might be similar in some ways to what is happening in Brazil, but also somewhat different as well, because of course in different parts of the world, there are different pressures, there are different, aspects that you actually have to consider. So I thought, maybe this would be useful in terms of understanding a little bit, about where we are headed in the UK and Europe. So this is an interesting diagram from, let me just, do this. This is an interesting diagram which gives the energy usage in the UK over several years. You see it's over the course of 4 years, and it's broken down into the different sorts of energies that are used. We have electricity, which is the red line. We have the black line, which is transport, and we have the blue line, which is associated with natural gas. Okay, and you see that there's cyclic variation by year. If you look at the electricity, there are these oscillations which are by week. On Sunday, there's less electricity used than others, and as you go towards winter, the amount of electricity increases until you get to Christmas, and there's actually a decrease of electricity over the Christmas break. Okay, and it sort of continues. And you also see the thing with a similar oscillation with natural gas. Okay, and natural gas, because natural gas is used as a heating fuel in the UK, but of course it's also used as in industry. And you see that the natural gas variation is actually relatively large. The peak and the trough is relatively large. And then we have some variation, some small variation of transportation, which is the black line. So moving forwards to a world in which we want to decarbonize everything. In principle, we can decarbonize the electricity because we have the opportunity to actually feed that electricity from hydroelectricity in Brazil, or from solar, or from wind, or potentially from nuclear. We can decarbonize that. But how do we decarbonize the rest? How do we decarbonize heating? How do we decarbonize transport? Of course, with the availability of electricity, we want to electrify as much of that as possible, but there still is a requirement for the use of chemical fuels of some sort. We have to ask where those will come from. So one of the positive things, so that's the negative thing, we need to decarbonize. One of the positive things is what's been happening to the cost of electricity. And specifically, I want you to look at the yellow line and the blue line. The yellow line is the cost of electricity. This is the unsubsidized, levelized cost of electricity. The y-axis is the year. So you see that we go from 2009 to 2021. And you see the yellow line is for solar electricity and the blue line is for wind. And you see that solar PV has seen a 90% decrease in the cost of that electricity over that period. And wind has decreased by 70%. At the same time, other sorts of electricity have actually increased. So you see something like nuclear electricity has actually increased. But the really amazing thing is that electricity from renewable sources is dropping, and it continues to drop, becomes cheaper and cheaper. So all of a sudden, the need and the ability to use electricity at a larger scale becomes quite important. But of course, we have an issue when we deal with renewable electricity and renewable electricity generation, at least if you consider wind. So this is what can happen in Europe. This is associated, these colors down here represent different sorts of weather systems in Europe. And I want to draw attention to the two green ones, the so-called European blocking and the Scandinavian blocking. And in these periods, what happens is that all of Europe, or over a very large part of Europe, the wind drops. Okay, and this tends to happen in the middle of winter. So you have very clear skies, the wind drops, you have very clear skies. And if you're relying on wind power to power your grid, you're going to be in trouble, okay? It's when you need a lot of electricity to heat in Europe, and all of a sudden the wind goes, the sky becomes clear in the middle of winter, and it starts getting very cold. These lines represent, the potential, these lines, these colored lines represent the potential wind power that you could generate. And you see in these green periods, it drops. And these green periods can last a few weeks. So we can see from this that potentially we need to store electricity for periods of days or even weeks for those periods when the renewable electricity is not available. And sort of here's an example, gas shortage fears and polar vortex threatens to plunge Britain into extreme cold crisis. Okay, so this is sort of the sort of thing that we're starting to think about. The other issue you have is that, and this is a slide from Professor Goran Strabak in Imperial College. The other issue you have is that as you increase the amount of renewable electricity going into your grid, especially if it's intermittent renewable electricity, your ability to utilize the grid, the capacity factor, decreases. So you have to build your grid, in order to actually handle all of that electricity, but some of the time you're not using the capacity of the grid because not enough is being generated. Okay, typically you want, if you build a long distance grid, you want to use it at maximum capacity continuously, get the most use out of it. So that means that typically you might have periods where, as you increase the amount of wind penetration in the UK, you might get periods where you can't use all of that electricity. Okay, you could generate the electricity, but it's not possible to use it because you can't distribute it. And under these conditions, you have what's called curtailment. You have to tell the wind generator, I'm sorry, we can't use the electricity at the moment. You're generating too much. We don't have enough use for it, right? And you throw that electricity away. So that's the flip side. That's also not good. So what can we do about it? Well, of course, we need to use storage of some sort. We need to store electricity. And at the moment, if we just concentrate on this right-hand side, this blue one here, the major way that we can store electricity at scale is to use pumped hydroelectric power. Okay, and across the world, there's about 170 gigawatts of pumped hydroelectric storage available. To put that into context, the entire world's electrical power usage is about 2.5 terawatts. Okay, so there's about 160 gigawatts. There are other sorts of storage things down here. There's thermal storage, electrochemical storage, and electromechanical storage, and they're broken down into here. So thermal storage, here's electrochemical storage, which is basically storage within batteries. And here is electromechanical storage. I should say this plot is from this ARENA plot. But this is what the situation was in 2017. The predictions is that by 2030, pumped hydro will increase by 38%. Okay, so that's a significant improvement to 235, but it's still small compared to world electricity usage. The really interesting thing is what happens to electrochemical storage. Electrochemical storage, predominantly in batteries and other electrochemical systems, will increase tremendously. In fact, the predictions are that by 2030, the amount of electrochemical storage will match where pumped hydroelectric storage was in 2017. Okay, because this gives us a way to actually store those electrons, but still not at the scale we need. We need to store electrons at least 100-fold, if we're going to last for those periods when we don't have electrons. This is temporary message, temporary way of doing this, but it's by no means enough. So let's consider what we might be able to use beyond those simple batteries. Okay, well, here is pumped. So this is what's known as a Ragone plot. And the Ragone plot along the x-axis, here, you see it's a logarithmic scale, is the power density. That is for a given mass of equipment, how much power can you produce? The larger the number, the more power the equipment, the system can actually produce. You see that each time it goes up by a factor of 10. And along the y-axis here is the energy density. That's how much energy for 1 kilogram you can store in the system. Okay, and you see pumped hydroelectric is down here. Pumped hydroelectric has a really quite a low power density and also a low energy density. That's why when we have hydroelectric systems, they have to be very, very large. Okay, just because the energy density is low and the power density is low. Of course, what we want to do is we want to be up in the right-hand corner here. We want to have high power density and high energy density. Okay, so that we can, store a lot of energy and be able to extract that energy very quickly as well when we need to. We also need those energy systems to last a long time. So these lines here tell us what the characteristic time associated with charging and discharging that specific technology is associated. So we have something like supercapacitors, which have very high power density, but relatively low energy density. And you see that they only last for around a few seconds. Okay, so supercapacitor is useful, can provide a lot of power, but only for a relatively short time, only for a few seconds. And if you remember, what I said is that potentially we need days to weeks worth of power storage. So we need to think about those systems that are in this region here. So you see here's pumped hydroelectric. Here's fuel cells and electrolysers. This is about taking that renewable electricity, producing hydrogen, and then converting that hydrogen back into electricity. Potentially that can also last for hundreds of hours. And the other area, which is sort of starting to approach that, is things like flow batteries. And I'll talk about these in a little bit more detail. You'll see that something like lithium batteries is a little bit further away. So lithium batteries are useful, but at the moment they're too expensive. You'll also see that the color coding here represents the relative cost of the energy stored. So that we see something like lithium batteries are relatively expensive, flow batteries are less expensive, and fuel cells and electrolysers and pumped hydroelectric are less expensive still. And that's the other thing we have to consider. It's not only the ability to store the energy, it's the cost. It's also these other aspects here as well. Calendar life, that's how long the system lasts. Okay, ideally 10 years, 20 years, 30 years. Think about a hydroelectric dam, can last 100 years. That's very good. Cycle life, that's how many times we can fill and empty the store. And that can be quite important, from lithium-ion batteries. Eventually, the lithium-ion, after charging and discharging, a lot of time, your phone starts to not being able to store the charge. Okay, so the number of cycles you go through can be very important as well. The efficiency, resource usage, we'll talk a little bit about resource usage. If we're talking about using something at really large scale, we have to start thinking about the elements we're using in it, because maybe there's not enough. Toxicity, okay, again, these are going to be big systems. Okay, so they can't be toxic. Recycling and cost. So the other thing to note is that as we develop technologies, the price of those technologies comes down. So this is a plot, from this paper here from Ian Staffel in Imperial College, where along the x-axis, again, this is a logarithmic plot. This shows the cumulative installed capacity. That is the total amount of electricity storage that has been created in the world. Okay, so as we go along, we make more and more, year by year, we make more and more. And the y-axis is the cost of that storage per amount of energy stored. And what you see is all of these curves go down. That's because as you make more storage, you learn how to make it better. You become more efficient at it. So the cost of that storage comes down. And these are all for different sorts of electrochemical systems. So you see, this blue one here is for lithium-ion batteries, grid-scale lithium-ion batteries. You see this here, this green one here, is for pumped hydroelectric storage. You see, pumped hydroelectric storage is not going down in cost. That's because it's technologically mature. You know, you can't really improve the efficiency of it significantly. You know, when people make dams, they make them, you know, the cost doesn't really decrease. The yellow one here is lead acid batteries. You might be surprised to know that a lot of lead acid batteries have been made in the world. And just to give you a calibration point, this dashed line here represents the world daily electricity usage. Okay, 1 day of electricity, you know, if you want to store 1 day worth of the world's electricity, you have to have a technology that gets up to that line. Okay, so we don't have any technologies that get up to that line. Maybe all the lead acid batteries that have ever been made, you know, are sort of getting close. Okay, but the interesting thing you note is that all these lines are coming down, and they're coming down quite quickly. Yeah, you know, typically about 10 to 15% per factor of 10. So every time we make 10 times larger amount, the cost comes down by about 10 or 15%. Okay, that's important because it means the technology is getting cheaper. So I want to talk a little bit about resource utilization. That's the other thing we have to think about, because if we really are going to make something at the scale to store the world's electricity for days or weeks, we have to think about the amount of material that's used within the system. You know, we have to think about, you know, this plot here shows us the world's elemental abundance in the Earth's crust. And of course, we've got, you know, some metals up here, rock forming, which are present at large amounts, iron, titanium, manganese. We'll talk about manganese later on. You know, then we've got the rare earth elements here, and then we've got the rarest elements, the platinum group metals here. What this plot on the right-hand side does is it lists all the different possible, or not all, but many of the different possible battery chemistries we can think about. Okay, if we're talking about thinking about batteries trying to store energy. And this yellow one is the annual production. Okay, now this dashed line, dashed line that I put over the top, is the world daily electricity usage. So if we want to store 1 day's worth of electricity usage, okay, we would not produce enough of all of the chemicals if we used all of the world's production, okay, of those elements, we would not be able to produce 1 day's worth of electricity storage. There's only one chemistry where we would, and that's sodium sulfur batteries. So that's in terms of current production. Of course, you can increase production. The other question you might have is, well, what about the total amount of those elements that exist? Yeah, and that's what, you know, if we look at the total, all of the elements for each of these chemistries, you can see there are some chemistries here. If we want to store one day's worth of world electricity, there's some chemistries here that actually there isn't enough of those elements in the Earth's crust, right? So we can rule out those chemistries as, you know, you're not going to be able to store that sort of scale. There are some which look maybe somewhat more reasonable, you know, something like. And then the last one is about how much those elements cost. Because of course, if we're going to build these systems, we have to do them, you know, in a low cost way. And so really we need to be at or below this red bar in terms of the battery cost in order to store that electricity. If it's on the right-hand side of that bar, the battery's just going to cost too much, just in terms of the elements that are used within it. And that severely reduces the options we have in terms of electricity storage. So I want to return to hydrogen because, of course, if you remember, hydrogen's all the way up here, right? We've got lots of hydrogen. Okay, it's stored in water, you know, think the world's oceans, potentially lots of hydrogen. So what about using hydrogen as a way of storing? And of course, hydrogen can be viewed as a systems fuel. We can do lots of things with hydrogen. Okay, we can burn it to make heat. We can put it into internal combustion engines. We can put it into fuel cells. We can use it for industrial production. Most of the world's hydrogen produced nowadays is used to make ammonia. 30% of the nitrogen in your body comes from the Haber-Bosch process, right? At one point, you know, it was a nitrogen molecule and a hydrogen molecule in a reactor, you know, that was used to make ammonia, and that ammonia was then spread on the land somewhere, you know, grew some plants, which you then ate, and that ammonia went into you, and actually, you know, that nitrogen went into you and was incorporated in your body. It's surprising to think, right? 30% of the nitrogen in us. So the thing about hydrogen is it can do all of these things, but it isn't the best at any of them. Okay, if we look at one example, if we say look at small scale electricity storage, well, batteries are much better at small scale electricity storage. Okay, if we look at heating, well, hydrocarbons are better to use if you're going to heat, right? But the interesting thing about hydrogen is, although it's not the best at anything, it is second best at a lot of things. And that's why hydrogen is potentially a system fuel. Hydrogen can be used for lots of things, not just one. That then gives a benefit. So I just want to talk a little bit about the UK hydrogen strategy. So what the UK views. So the UK published a hydrogen strategy in 2021. It talks about producing a lot of wind, you know, a lot of wind power, a lot of wind electricity, and using that in electrolysers, but also to produce what is called, so that's going to be used to produce green hydrogen, but also to, you know, using natural gas to produce what's called blue hydrogen, where they sequester the CO2. And the UK, you know, the UK hydrogen strategy says that by 2050, somewhere between 20 to 35% of primary energy usage will be in the form of hydrogen. Okay, that's a lot. Okay, that is, you know, you can see the numbers here, that's 400 terawatt hours. So the question is, where's that hydrogen going to come from? So in the short term, you know, the idea is that some of that hydrogen is produced in electrolysers. Some of it is you know, here are the electrolysers. Some of it is produced from natural gas. The hydrogen then starts getting distributed through gas networks. And as we go to late 90s and mid 2030s, we increase the number of electrolysers. And we also have a certain amount of blue hydrogen that's produced as well. You know, and so we go on towards. Now, in this initial, you know, August 2021, the UK hydrogen strategy, they talked about 5 gigawatts of low carbon hydrogen. Low carbon hydrogen includes blue and green hydrogen. That is hydrogen that doesn't produce any CO2. Moving forwards, just a few months later, the net zero strategy not only mentions the 5 gigawatts of low carbon hydrogen, but then starts to talk about electrolysis, how electrolysis is important. And then in April 2021, we double the amount of low carbon hydrogen. So you can see that there's a strategy here. Each time they release a report, it's actually got more low carbon hydrogen in it. And now there's a discussion, you know, 10 gigawatts of hydrogen with more than 5 gigawatts of green hydrogen. Okay, so already, you know, this is talking about rolling out electrolysers to actually take that electricity and create green hydrogen. So how do we create green hydrogen? Well, we use water electrolysis. Water electrolysis is you know, the original technology is very old. You know, it started in 1927. Okay, this was a Norsk Hydro. This was in Norway, and they used hydroelectricity to electrolyze water to produce hydrogen. That hydrogen was then used to produce ammonia on site, and then the ammonia was shipped away. In fact, nowadays, the largest amount of electrolytic hydrogen produced from electricity, is not produced by electrolysis of water. It's produced in the chlor-alkali industry. It's produced as a co-product during the generation of chlorine. And here's an example. This is Ineos. This is in the north of England. Here's what a electrolyzer looks like. This takes a solution of salt, sodium chloride, and electrolyzes it to chlorine, sodium hydroxide, and hydrogen. Okay, and these have 3.5 square meter electrodes. Here's the reaction that occurs, and here's a cell hall. And each of these reactors is, these are large. Okay, these produce a lot of hydrogen. Now, the point about hydrogen production is about 2/3 to 4/5, between 67% to 80% of the cost of that hydrogen you produce an electrolyzer is just the cost of the electricity. Okay, so the majority cost is associated with electricity. And if you remember me going, talking right at the beginning about the tremendous reduction in cost of renewable electrons, this is the reason why all of a sudden hydrogen production and electrolyzers starts to become a really significant option, because the cost of those electrons is actually decreasing really significantly, much less than the cost of electrons from hydrocarbons. Previously this wasn't the case. It was the other way around. Making electricity from hydrocarbons was actually cheaper than renewable, but now it's swapped. So all of a sudden, the possibility of producing hydrogen happens. So there are different sorts of chemistries. We have alkaline, which is the one, that goes all the way back to 1929. There's PEM, which was developed in the 50s and 60s for nuclear submarines originally, and also for NASA. Then there's solid oxide, which is a high temperature system. Sorry, it says, oh yeah, no, I've got those swapped. And then there's alkaline exchange membrane. I've just noticed that the 700 should be with the blue one and the 100 should be with the pink one at the end. Okay, so and as we go down there, we go to decreasing technological maturity. Just to give you an idea of what liquid alkaline electrolyzer looks like. Here's this one, Norsk Hydro in Norway, 1929. It consumed 167 megawatts of electrical power. These are big systems, okay, producing a lot of hydrogen. This is what a module looks like today. Typical modules consume about 100 megawatts of electricity. It's a lot, okay? You can have a smaller one. Here's a 50 kilogram a day hydrogen system. If you consider the polymer electrolyte membrane electrolyzer, these are much newer, but you have small systems. The nice thing about these technologies is they scale, okay? Even when you go to very small systems, they still maintain high efficiency. So you can have a small hydrogen generator here, you can have a somewhat larger one, 1 kilogram per day, or you can go to something like a larger system, where the modules are about 2 megawatts. Each module is about 2 megawatts, and you have multiple modules. Okay, so 2 megawatts corresponds to about 1 ton a day of hydrogen running continuously. And just to compare the PEM electrolyzer to the traditional alkaline, the difference is the PEM electrolyzer can operate at much higher intensity, okay? Or, if you will, at the same current, at the same intensity, it operates at much higher efficiency, okay? So with a proton exchange electrolyzer, your intensity is actually shrunk down. You can actually have a much smaller system to produce the same amount of hydrogen. And if you just go back and look at it, here's the 2 megawatt, 1 ton per day system for the PEM electrolyzer, and here's the one for the alkaline electrolyzer. You see, there's a big difference in size and scale. The solid oxide electrolyzer operates at high temperature, and these are much less technologically advanced. The largest module is about 250 kilowatts. And the last, the one that's the least developed, is the so-called alkaline polymer electrolyte electrolyzer. So these are very similar to these use a solid polymer, a solid plastic, and they're relatively simple. And the benefit of these systems is that they don't, as with the liquid alkaline, is that they don't use materials that are resource limited. So just to give you an idea about how electrolyzer capacity is increasing. So nowadays, everyone wants electrolyzers. Okay, throughout the world, the opportunity to actually convert renewable electricity to hydrogen is growing tremendously. So this is the growth in. So this is not the growth in electrolyzers. This is the growth in manufacturing capacity for electrolyzers. Okay, so 60 gigawatts per year by 2027. Each year you can produce 60 gigawatts more of electrolyzers. This is tremendous capacity that's growing very quickly at the moment. Now to talk just quickly in the last few minutes, just a little bit about the work that we're doing at Imperial College to try and facilitate, this generation of hydrogen, in these electrolytic systems. At Imperial, we are developing new catalysts, not only trying to take precious metal catalysts and actually improve their activity. For instance, here's catalysts that we're looking at for water electrolysis, but also looking at non-precious metal catalysts, how we can actually utilize materials that don't use relatively rare elements in them in order to facilitate these chemical transformations. The other area, which I talked a little bit about here earlier on today, is all about designing better electrodes. Being able to design electrodes that allow higher intensity operation so that we can shrink the size of these electrolyzers. Okay, because it's very important to make these electrolyzers as small as possible. And the final example is maybe a sort of a change in attitude to say, well, instead of electrolyzing water to produce hydrogen and oxygen, maybe we can turn these systems into a different way of storing electricity. And that's what we call a redox fuel cell. Okay, so the real problem, when we take water and we electrolyze it, is that we have to produce oxygen at the same time. And actually the same thing happens in a fuel cell. You have to combine hydrogen with oxygen. And it turns out the oxygen reaction is a really difficult reaction. It's the one that requires the most catalyst. It's the one that's the most inefficient. So the idea here is we get rid of the oxygen reaction and we replace it with something else. In this case, we call it X. Okay, so we produce hydrogen and X. And then if we want to make electricity, we can go the reverse way. We can take that hydrogen, combine it with X in an electrochemical cell, and actually generate electricity. So this is the opportunity to make a large-scale battery in which our energy is stored in hydrogen and some sort of redox species. And we've done a lot of work in this. And in fact, we've found a manganese couple, which we just show here. And this manganese couple is based around manganese, which is a very ubiquitous element. If we go all the way back, you'd see that manganese is number 12 in the Earth's crust. Okay, so there's lots of manganese available. In each of your homes, you've probably got 1 kilogram of manganese. The little AA batteries that you have in your remote controls, they all contain manganese. So you've probably got 1 kilogram of manganese dioxide in your. So using manganese, we're using an earth abundant material. Okay, and because we're producing hydrogen on the other side, we actually have a system which, which potentially we can scale up to the scale that we need. And, that chemistry is now spun out into a company. It's called RFC Power. Here's what our electrolyte looks like. It's sort of a beautiful deep, when it's charged, it's a beautiful deep sort of purple color. And when it's discharged, it goes clear. And we've shown, significant, hundreds of cycles over many months of operation. So I want to finish now. What I've talked about is the opportunity to store these electrons in hydrogen. Is this a new idea? Well, no, it isn't. Okay, Jules Verne, okay, 1874, in his sequel to 20,000 Leagues Under the Sea. This was the book that he followed it up with. Okay, Mysterious Island, talks about using hydrogen as an energy vector. Okay, all these years ago. Okay, so And what will they burn instead of coal? Water, replied Harding. Water, cried Pencroff. Water is fuel for steamers and engines. Water to heat water? Yes, but water decomposed into its primitive elements and decomposed doubtless by electricity. Okay, there's our electrolysis. You know, that hydrogen and oxygen, which constitute the water, used singly or together, will furnish an inexhaustible source of heat and light, of an intensity of which coal is not capable. Okay, and it sort of continues, you know, water will be the coal of the future. I should like to see that, observed the sailor. You were born too soon, Pencroff, returned Neb, who only took part in the discussion in these words. So, yes, in 1874, he was born too early. Maybe you are not, right? You'll get to see this happening finally, as Jules Verne predicted, you know, so many years ago, over 100 years ago. So thank you very much. And that's me done. I'm happy to take questions.
Acho que tá ligado agora. Okay, thank you for this nice presentation. If you allow me, I would like to open for discussions and questions. Yes, Cássio.
Hello, I would like to ask what is the kind of electrolyzer that you think that would be better for hydrogen production as a commodity? Because it seems like nowadays we will face a new kind of boom of commodity, mainly here in Brazil. And I think hydrogen will be like a commodity for us. So I am more curious about it.
I mean, that's a very good question. Okay, so if we think, you know, here are the different chemistries. Okay, if you want hydrogen as a commodity, you need to have something which scales to large systems at the moment. And really, there are, at the moment, currently, there are only two systems, you know, that are in the offing. The alkaline one, which is the one on the left, which is the historical one, you know, this one, 1927, up there, and the PEM one. And they have trade-offs. The PEM one is very good. It can follow loads very, very well. So for instance, if you're coupling it to renewable electricity, right, where you might have, you know, the sun might go behind a cloud, the wind might stop, you know, you might have to shut it down and start it up again. The PEM is the best one. And it's also, you know, very high intensity. So you can actually site it at different places really well. If, however, you've got a continuous power source, then the alkaline one. Over the longer term, I would say the alkaline exchange membrane one offers some better opportunities, but it's still relatively early in its development life. And maybe the solid oxide system as well. But again, that is very early in its development life. So it's unclear whether these latter ones will be able to grow large enough before these other ones on the left-hand side grab all of the market. Certainly when I talked about, you know, the manufacturing capacity, all of that manufacturing capacity is in the first two. Yeah. So one of those two. It depends how you're going to site and how you're going to operate it. Yeah.
Okay. More questions?
Thank you. Okay. You said before that the polymer electrolyze, it's something like the pen, but it's less stable, right? So what is the advantage of studying the polymer electrolyzer if it's less stable than the proton exchange?
So, okay, so the benefit of the alkaline exchange membrane materials, at the moment, it is less stable. It is earlier in the development cycle. Okay, it's not that it's necessarily less stable, but it needs more scientific work. The benefit is the difference between using a liquid as your electrolyte and using a solid polymer, which is like a plastic sheet, a clear plastic sheet, in which you don't have to have any liquid sloshing around, or at least no liquid electrolyte sloshing around. And the benefit of that is that you can actually go to typically you can go to higher currents, higher intensity, and you can typically also follow loads better. You can actually change the power input very quickly for those sorts of systems, much more so than with the liquid. And the other benefit you have is that you can operate them at higher pressure. So you can generate your hydrogen typically at a higher pressure than you can with the liquid system.
Anthony, what about hydrogen storage? Could you comment about hydrides or carrier that you think could be?
Did you see my slide?
Promising?
Next slide along, okay? So yeah, I mean, hydrogen storage is a really interesting area, okay? So this graph compares different ways of storing hydrogen, okay? I didn't set him up to ask that question, by the way. So along the x-axis, you have what's called the gravimetric hydrogen density. That is, for the given storage, the amount of hydrogen stored per mass of material. And along the y-axis is the volumetric. It's kilograms hydrogen per cubic meter. And of course, where you want to be is you want to be in the upper right-hand corner, okay? Because that means you're storing, for weight, you're storing a lot of hydrogen, and for volume, you're storing a lot of hydrogen. This dotted line here corresponds to liquid hydrogen. So liquid hydrogen is, of course, 100% hydrogen. It's all the way off to the right. Gravimetric, 100% of the hydrogen, so it's 100% weight. And this is the volume. This is the volume of liquid hydrogen at minus 259 Kelvin. Depending upon the size of your tank and how much your liquid hydrogen tank weighs, you will follow this curve. Okay, if your tank weighs, 90% and it contains 10% hydrogen, this would be your, volumetric. Okay, so this is for liquid. For compressed hydrogen, you follow these curves. Here's for a compressed hydrogen in a steel cylinder. Here's compressed hydrogen in a carbon fiber composite cylinder. Here's where the Toyota Mirai, where it's compressed hydrogen. So that's the weight of hydrogen stored within the cylinder. Stores about 6 weight% hydrogen. It's pretty good, actually, 6 weight%. You'll see that 6 weight% hydrogen is actually better than formic acid. Okay, that's more high. So that's actually storing more hydrogen than formic acid. Okay, so you can see other chemicals maybe of interest for Brazil is ethanol is up here. Okay, so ethanol stores about 13 weight% hydrogen, and it's also got a good volumetric energy density. And as you mentioned, there are these metal hydrides. These metal hydrides store a lot of hydrogen in them. Okay, volumetrically, they're much better, twice as good as liquid hydrogen. Okay, because the hydrogen is much closer within the metal lattice than it is in the liquid. However, the gravimetric energy hydrogen density is really poor because, of course, you've got to carry around the metal, which actually weighs a lot. So only stores relatively little. And of course, we have things like methane. Here's methane. Here's ammonia. Ammonia is also considered to be a liquid. But of course, if you're really going to store hydrogen on a large scale, what you want to do is you want to store it geologically. Okay, you want to store it in a cave. You want to store it underground. This is actually really well understood technology. For instance, in the UK, there's a map of the UK, and where you see those blue regions, these are where there are salt caverns, where you can actually, where there are salt domes, you can go down and you can actually make caverns, and you could store months worth of hydrogen in the UK in these salt caverns, and they're very, very inexpensive to make. So they're okay. Yeah. So yeah. I hope that answers your question.
Sure.
Yeah, I did both small scale and large scale.
I was just wondering about the comparison between methane and formic acid, but it was clearly explained. Yes, that's very interesting. Thank you. Very nice. Questions? Yes, sir. Nadine.
Sir, I'm working on hydrogen fuel cells, proton exchange membrane fuel cells, in which we are substituting iron, the noble metals for iron.
Yeah.
So I'm working on iron-based proton exchange membrane fuel cells.
Yeah.
So actually, these catalysts are going to shake hand with the platinum-based catalyst. So what do you expect about the future of the iron-based catalyst for the incorporation of oxygen reduction, which is the area of my interest?
Sure.
So
Oh, yeah.
sorry.
Yeah. It's also an area of my interest as well. So, so of course, you know, that's these catalysts here. Okay, so we are doing work on those catalysts as well. We're really interested in them. You know, to my mind, it's surprising how well the performance has improved over the last few years for these catalysts. And you're right, they're almost shaking hands with platinum. They're getting up to the stage, not quite, but you know, you can actually start getting reasonable performance out of these systems. You know, as you know, one of the big issues with these catalysts is their stability at the moment, and this is something we need to work upon. So I think performance is getting to where they need to be. Now we need to work on stability, and I think the opportunity to think about how we can also take what we learn from these catalysts and make them into electrolyzer catalysts would be really useful as well. You know, because these catalysts are much more similar to enzymes than they are to normal classical, you know, platinum, you know, particle catalysts. And the question is, how can we use that knowledge in order to develop better water oxidation catalysts? Yeah. Thank you.
Not sure if people that is watching online this talk, if they have some questions, I cannot hear from you guys. Not sure if they. Yeah, sure.
Hello, sir. Sir, the recent research has been focused on development of bipolar membranes. So what about the current status and the future status of the bipolar based electrolysers, water electrolysers?
Okay, so the question is a much more of a technical one about bipolar membranes, and bipolar membranes are a specific class of membranes where you put a cation exchange membrane next to an anion exchange membrane, and these have classically been used in salt splitting applications and also in water purification applications. And the question is, you know, do these have a use in these sort of electrolytic systems? And I think they do. I think there's some really interesting work because, of course, using these membranes, you can operate with a pH gradient rather than operating at the same pH on both sides. So this gives you some opportunities, maybe in terms of the catalyst. But the real issue with these is, of course, what happens at that interface between those two membranes and how you split water into a proton and a hydroxide efficiently and at sufficiently high rate. And this is the real issue for those systems at the moment. But I agree, I think these are really interesting from a technological viewpoint, development viewpoint. Those are really interesting materials.
Okay, thank you. Okay, see if we don't have any additional questions, let's thank the speaker again. Okay, just finish.
Thank you.